All right, so here's another video. I want to walk you through the three-phase balanced 6-2 exercise that uses, now we're not using purely resistive load, we're going to have some reactive value in there, and the lab has you build one that puts a capacitor in parallel with each one of those single-phase resistors. And so now we know that if we have some Y component to our circuit, which that's going to be that impedance value, or the Y component is going to be the capacitance value in there, and the X component is that resistance, we're going to have an impedance value in there now. So it changes how we need to attack figuring out each one of those single-phase power calculations. However, it's a lot of the same. The summative properties of the powers in the single-phase system are all the same. The only difference now is if I have a force, a kid pulling this way and a kid pulling this way, which is my capacitor and my resistor, now I got to figure out where am I actually going before I can start doing the simple single-phase Ohm's law stuff. So to do that, I drew up the wiring diagram here, and I also have it built over here already just to speed things up. This is the exact same one that I did for the purely resistive load. The only difference is I added capacitors. So I put them in parallel. And as a matter of fact, through a little bit of math, nerd work, and science, I need to make sure I update my values up here. 1200, 1200, and 1200. All right, so what I do is I have capacitors set in there with a reactive capacitance set to approximately 1200 ohms, and my resistors are set to 300 ohms, and so now I'm just going to go through the calculations before we do the exercise like previously. So what I'm going to do is well, I know I need to figure out what is the result of these two forces on the circuit. I also need to see that these are in parallel with one another. Am I correct? They share the same two common nodes, and so the impedance formula for a parallel circuit is going to be R x sub c, R times x sub c, over the square root of R squared plus x sub c squared. All right? And then also the phase angle that I'm going to get as a resultant of that now, because it's a parallel, is going to be the arctan of negative R over x sub c, which this is a little opposite of what we were doing in the series circuit. So again, that's why it's important to note that we see this parallel connection between these two, so this is the two formulas that we have to use. If this was a series connection, which you're going to build that as well, then you're going to use a complete separate formula. All right, but this is for a parallel one. So what I'm going to do now is I'm going to set up my impedance formula here, and I'm going to say, okay, well, if I've got 300 ohms times 1200 ohms over the square root of 300 squared plus 1200 squared is going to equal Z, Z being my impedance. All right, so I'm going to go through and calculate that. So I have, let's say, and again, working with your calculator is kind of an important step so you understand the order of operations your calculator works in, which should be the right ones. But if you use parentheses when you're doing your calculations, it can help you out, or you just got to keep track of it. So I'm going to go through it kind of slow, just so you see. So 300 times 1200 is going to equal 360,000. So we've got 360,000 divided by, now I'll do the bottom one, which I'm going to hit 300 x to the 2 plus 1200 x to the 2 equals, then the square root button, and I get 1236.9. All right, so now I'm going to say 360,000 divided by 1236.9 equals 291. And again, I'm rounding, approximately 291 ohms. So what does that mean? Well, that means that when I've got the kid pulling this way on that circuit and the kid pulling this way on that circuit, the actual, force, the vector that's the direction I'm going and the magnitude of it is actually 291 ohms worth of total opposition in that single phase circuit. So now that I have this value, I can do a couple of things. Now I can go back like in the resistive circuit and I can say, okay, well, I'm going to just figure out the current. Then I'm going to use the current and figure out the power. Or I could use that value to figure out the power. It's either or, we'll do both. So I'm going to say we know we're going to attack this, again, single phase, because this is a single branch off of here. So I'm going to do 120 volts divided by 291 ohms equals, and this is going to be what? Current, power, what? Current, right? So 120 divided by 291 ohms. 120 divided by 291 ohms equals 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 120 divided by divided by 291 is equal to 0.412. What does it say? 0.41 amps. Now I'll just use a different convention. I'll use this same numbers and I'll get my power by just squaring the top. So if I do this value, 120 volts divided by 291 squared there, I'm going to say 120x squared divided by 291. And I got 49.48, so I'm going to say approximately 45, let's say 49 watts. Okay, so those are almost the same calculations we had with the other one, right? All right, so now we'll do the same thing. I'm going to sum the values here. All right, and I'm going to say 49 times 3, because it's a balanced three-phase load. 49 times 3 equals 147. So 147 watts. That should be my total power there. All right? Is that it? Is that real? Man, we didn't take into account cosine theta in there though, did we? We sure didn't. All right, so now when we do these calculations here, when we're doing this power and we're just saying volts times amps, or volts times the current without taking into account that phase angle difference, then we're actually saying that's the VA, that's the apparent power that's in there. But what's the actual real power that we're getting? Well, there's going to be a phase angle relationship associated with that impedance value, which is then in turn going to translate into your power factor. So now let's look at back up to here to what the phase angle is. Well, if I take R, negative R, which is going to be R 300, yeah, and then divide that by, where are we at? Our total X sub C, which was 1200, equals, and I'm going to do the arctan of that, second arctan, and I come out with a negative 1403 degree angle, negative 14 degrees. So if I was to vectorially draw that out, all right, then that means R going this way, X going this way, my resultant vector, right, that's coming right here, is actually, if I move this head to tail and then I draw my resultant, this angle is going to be 14 degrees. Cool. All right, so what does that mean? Well, now if I know that that's going to be my phase angle, now I can do cosine theta. And so the cosine of 14 degrees, let's say 14 cosine, equals 0.97. What is that cosine theta? What is that 0.97 I just calculated by doing that? What do we call that? Power factor, you're right. Okay, I just did it in an inadvertent way. But what I did is I solved for the phase angle of this impedance value. So what that means is that's 291 ohms at negative 14.03 degrees. All right. And what that also means is that this theta here is going to be our theta that we can use in calculating. And there's some proportionalities there that are going around that I'm translating that impedance value over. But that's what's going to dictate what our power factor is. So now, if we know that cosine of 14.03 degrees is 0.97, we can take this 49, it was 49.48, so I'll say 49.5, and I'm going to take that times cosine theta, cosine of 14, which was 0.97, and now I'm going to say times 49.5 equals 48.02. Now think back when we demoed this and remember what those values were. That's it. That's set to kW. So we're getting actually 48.02 here times 3. So our power should be approximately 100. This is VA. And because I just calculated this theta and now multiplied this times cosine of that, now I'm getting 144 watts. All right, so this is S, this is P. Cool. All right, now I'm missing one element from this. I got the S, I got the P. Can you think of the third part of that power triangle that I can calculate now that I've got the hypotenuse and the adjacent angle, or the adjacent side? That's right, the reactive power. You're absolutely on it. So the reactive power, the Q, we're just going to use Pythagorean's theorem for that. Right? Because it's the easiest way to approach this. We could use sine, we could use cos, we could use all kinds of things. Pythagorean's theorem is the easiest way. So I know if I have this power triangle here, and I figured out that my S is 147, and my P is 144, well, this is Q, and the lab is going to ask you to solve for Q, and I'm showing you this because this is an easy way to do it. So now you just need to use Pythagorean's theorem and say, well, if a squared plus b squared equals c squared, then b equals the square root of c squared minus a squared, which means the square root of 147 squared minus 144 squared is going to equal our Q. So let's do that. We've got 147x squared minus 144 x squared equals square root 29.5. So what that means is our Q, 29.5 VAR. So now I've just completed the power triangle. All right. Now this is for the system collectively. All right. This is for the system collectively. We can do this also with individual ones and sum them, and you'll see that too. So actually, if I divide each one of these values by 3, you're going to see what that is, right? So I mean, this is roughly going to be about 9.8 something divided by 3. It's going to equal 9.85 VAR per line up there. So now, I mean, if we go through here and we said, well, we had 49.5 for a single phase one, right? And then over here, our power was 48, what did I say, 48.02? Okay, now let's do that same math. Let's do the square root of c squared minus a squared, which is going to be the 49.5 x squared minus 48.02 x squared equals square root, and we're left with, well, I came out with 12, but I'm doing some rounding stuff in here. So anyways, you get the point. It's summative in nature. So this right here is really just I don't even have to ask what the lab is solving for because I just solved for everything in the circuit. So now if you approach these circuits like that, you attack them and you just solve for everything, which is cool in a balanced three-phase circuit because all you got to do is solve for one and you know that it applies to all three. If you do that, then, you know, ask me anything. I've already got all the answers. I just got to know where to get them on my scribble scrabble. So now let's build the circuit, which I already did. All right, and I'm going to get my awesome demonstrator, Mr. Dan Schwab, to come up, and he's going to operate the power plant for me, and we're going to test this out. So now that we've already got the wires gone, we should just be able to get our generator up, get it running to the synchronous speed and exciter field voltage that we need, and we should be able to see everything I just calculated up there. So what he's doing right now, he's just getting that speed right up to that 1800 synchronous speed, which is you need 1800 revolutions per minute on a 4-pole synchronous generator in order to produce 60 hertz. Some science there. Now he's dialing his voltage down simultaneously so we can get it right there at the consumer's needs, which is 120 volts, 60 hertz. You can see how thrilling this is to be a power plant operator, right? This is intense.
119.9.
I mean, we're almost there. That's fine. All right, let's look at what our currents are in each one of these. So, I mean, you can see over here that between I1, I2, and I3, we're roughly at 4.41. Kind of fluctuating because our system's fluctuating, right? Which is also reality. All right, everything is a function of time. So, we're about 0.41. Now let's go back to the board and see what we calculated. Scooch over just a little bit. 0.41. We did all this crazy scientific math over here, came back to 0.41, and now we validated it over there. So now, same thing. Let's look at what our power is. We calculated our power to be approximately 48.02 per phase. And we go back to those same things, and we're 48.07, 48.6. We're right there within fractional increments. But you can see that our system's jumping around right here. So in any given second, as a function of time, it's going to vary a little bit. But that is definitely within the realm of, I believe, science. Okay? And then also our summative powers down here, we have 144.5. Well, that's pretty cool. Another thing I can show you, if I change this, so we calculated our, what do we say, the VA first, right? We said that was the 147-ish. Well, I can click this P right here, and I can change it to S, and now I'm at 148.4, which I calculate over here about 147 point something or other, right? I can do the Q also, and I'm at, it's showing a negative value because it's indicating it's more capacitive, which kind of makes sense as to what we're doing. Then it's showing about 35.18. I calculated it out at 38. It's probably because of how I rounded when I did my Pythagorean's theorem piece, just to make the calculator easier, but we're right there. PQ, this is the total reactive power, so 35. I mean, I don't know about you, that kind of confirms some science and some math for me with reality, yeah? Let's look at that phase angle though on our phasor diagram now to kind of validate some other things. All right, so we came up with a 14-degree phase angle, right? 14 degrees. If we zoom in on those increments, you're going to see that that's a 14-degree phase angle. All right. The only difference is I put the negative sign on there, and I didn't also put the negative sign on the reactance value when I did it through there, so that's why I came up with a negative, but in reality, it's just that 14-degree offset right there. So right on, all of our math for the parallel circuits worked out. It all science, right? You convinced?
Yeah.
Awesome. Hope you're convinced, and I hope you watch this video because when you're struggling, right now there's a class over there doing this exact lab, and they're going to be struggling. If you watch this video, it'll give you a head start, and you won't be struggling so much. This is a lot of math when you work this out. It doesn't look like a lot because I did it really fast and I did it in one small little increment. But once you see that you only have to do it for one, and then it applies to all three because it's a balanced three-phase load, you're going to be winning. Now let me give you a little other nugget. Assume it's not a balanced three-phase load, and assume we have different values. Different values on these resistors. Maybe this is different, this is different. How do you think we determine the total power now?
You'd still keep it in phase, right?
Absolutely.
Just do the same math by phase, but you're just changing your formulas that you're using, like the 300 squared plus the 1200 squared is going to be different for each phase.
Absolutely. And so you're going to see a summative power at that point, right? So you're going to have different PQSs here, which then in turn, when you add those together, you're not adding three equal elements, you're adding three unequal elements. But now what are you going to do? Well, now I had different currents on each phase at that point, right? Which means now I'll see the current that the generator's seeing, that line current there, right? And we're going to see what, it's awesome. Awesome magic there, all right? But it's not hard. It's so easy. You just got to look at the little slices and attack the little slices, and you'll be good to go. This is probably, this exercise right here, I think, this 6-2 is probably one of the hardest labs you'll do in here. I mean, obviously, you see we've got a bunch of wires over there, and it seems simple when you just go, you know, but look at what you're actually doing. You're just building three simple parallel circuits off of a three-phase source. So all of these wires that we created down here just to generate our own power are the equivalent of if we would have just tapped off of this if it was plugged into three-phase power and then ran it up. Very, very simple. So with that being said, good luck. This is very important, very awesome, and you need to very much internalize this math and believe in it because this will help you moving forward. Thanks.